Hello, my dear students. Welcome back to the class. So, in our previous class, I had told you that I will show you the capacitors, resistors, and all, correct? Today I brought it. I'll show it to you, okay? See, this is nothing but called as a capacitor, okay? This is nothing but a capacitor. Then there are different types of capacitors. See, this is one more capacitor. Can you see here? This is one more capacitor. There are two legs for capacitors. One is nothing but positive, another one is negative. Can you see this? Is it clear? Can you see this clear? Is it clear? See? This is one type of capacitor. This is one more capacitor. There are two legs. Two legs for the capacitor. For this type of capacitors, there is positive and negative leg. See, can you see one white line here? This is negative leg. Here there is no line and this is nothing but positive leg. See here also, one line is there. So this is negative and this is positive. And also you can say the shorter leg is negative and the longer leg is positive. I'll show you one more type of capacitor. See, can you see this capacitor? Can you see? See, this is one more type of capacitor. See, for these capacitors, there is no positive and negative legs. Okay? Next. These are nothing but called as resistors. I'll show you the resistors. See, this is called as resistor. See, it was somewhat cylindrical in shape. Can you see this? Can you see this? Can you see this? Yes, this is nothing but a resistor. See, this resistor is having different color bands. Can you see which color in this resistor? Which color you can see in this resistor? See here, brown, black, brown again. So three colors and one more color is there here. That is, which color means? It's a golden color. I'm sorry. This is brown, black, brown and golden color. So there are four colors. So can you name these? Can you say me what is the range of this resistor? Can you code these colors? It's one of the homework for you. Please decode this color. Okay, brown, black, brown, and golden color. It is fine. You can, right? Okay. So shall I move further? Yes. In today's class, see, I said resistor is nothing but opposition for the flow of charges. Correct? Now what I want to say is, since it is the opposition for the flow of charges, whether we have to use some other outsource, that is external source, that I have showed you a resistor, no? Like this band, if you use only, then is it a resistor, or all the equipments it has its own resistor? Yes, all the equipments will have its own resistance. We don't want external resistance. These external resistances are used to increase the resistance, that is to increase the opposition. So what I want to say is, every conductors or insulators or semiconductor is having its own resistance. Correct? Just like you people, you just see, all are not equal. All are not equal in all the matters. One might be good in studies, one might be good in sports, one might be good in the traditional dances or singing, one might be good in Western. Correct? So each and every one is not same. Those who are good in studies may not be good in dancing. Those who are good in studies may not be good in singing. Or those who are good in singing may not be good in dancing. Correct? In the same way, just like you have your own resistance, all the conductors will have its own resistance. Is there any help from its own resistance? Yes. If it is having higher resistance on its own, then it will develop heat. And that is why you are using iron box. Iron box, in that we have higher resistance objects we will use, so that it will produce more heat. How more heat will be produced? See, when the object is heated, what is happening? More number of collision takes place. When the collision in between the electrons, if the collision is more, then what happens? Then more heat energy is produced. In this way, we can increase its resistance. See, as the resistance increases, heat produces more and more. Now, one more thing what I want to say is, or else we can use external aid to increase the resistance. Is there any loss if it is having a resistance? If the object is having more resistance, there is a loss also. For example, if we use a wire of having a higher resistance, and if you use it for your household purpose, that wire, there is more power loss. Because resistance is more, right? So you have to use a wire, or you have to choose a wire in such a way that it is having a low resistance. If the resistance is low, higher current flows. Correct? More amount of current flows, and it is very helpful for you. If resistance itself is high, less amount of current flows reaches to you, then it is a loss for you. Correct? So, the word called resistance, what is the resistance of that particular object, you should know. If you know that, only then you can use it. Otherwise, it will be a big either loss or a profit if you don't know the resistance. So, as and how you want, if you will go and buy, no. You will just check out whether it is having high resistance or low resistance. Some of the equipments will have low resistance, but the costly may be very, very high. Cost. So, when you choose an object, you will go and see even cost as well as the resistance. Next. Now, so I said there will be a power loss in a resistor. So now what we are going to do is, we are going to find the expression for power loss in a conductor. Expression for power loss in a conductor. Expression for power loss in a conductor. Let us consider a conductor, okay, carrying the current I. Carrying the current I. Let us mark this point as A and this point as B. Let V of A be the potential at A and V of B the potential at B, such that V of A is greater than V of B. Potential at A is greater than the potential at B. So the electrons will always flow in this direction. Therefore, the direction of current is this. Understood? Because electrons flow from lower potential region to higher potential region. Is it so? Okay. Now, always the electron flows from higher potential region to lower potential region. Now, what you have to do? Now, what I want to say is, What is the potential energy at A? What is the potential energy at A? The potential energy at A, shall I write it as UA, is equal to, we have derived an expression, we know what is the potential energy. Potential energy is nothing but potential into charge, correct? If delta Q is the charge, then potential is V of A. Potential energy at B is charge into potential at B, because U is equal to QV, correct? This is expression for potential energy. Next what I want to speak about is, if we said delta Q is the charge, then can I say I is equal to delta Q by delta T, where delta T is the small time interval, correct? The time interval for the flow of charge from A to B. Okay. What is the change in potential energy? Change in potential energy is delta U potential is equal to UB minus final potential energy minus initial potential energy. So final potential energy is delta Q V of B minus delta Q V of A, correct? Delta Q is common, V of B minus V of A. Let V of A minus V of B is equal to B, is equal to V. This implies delta U potential is equal to delta Q minus V, correct? Am I right? Therefore, I can say delta U potential is equal to, that is change in potential energy is equal to minus delta Q into V. Delta Q into V. But what is delta Q? Can I say delta Q is nothing but I into delta T? Now if I substitute here, I'll get U potential is equal to minus I delta T into V, correct? I delta V into T, delta T into V. If there is no collision, if the charges are moving without collision, according to conservation energy, if the charges are moving without any collision, then according to conservation of energy, I can say potential energy, kinetic energy is equal to potential energy, but in the opposite direction, correct? If there is no collision, that is between the charges, if there is no collision, if it is moving without collision, then according to conservation of energy, change in kinetic energy is equal to change in potential energy, but in the opposite direction, correct? Minus. So therefore, now what I can say? Potential. If it is so, then it becomes plus IV delta T. Same. IV delta T. Why IV delta T? Because according to conservation of energy, if there is no collision between the charges, then kinetic energy is equal to potential energy, but minus of. When it becomes minus of, this becomes plus. Correct? Next. But in reality, when there is an electric field, the charges undergo collision. This is possible if there is no collision. If no collision, But if collision is there, then what happens? See, once again we will explain. Let us consider a conductor having the current or carrying the current I. Let VA be the potential at A and VB be the potential at B, such that VA is greater than VB. Potential energy at A is delta Q into V of A, where delta Q is the charge in the conductor. UB is equal to potential energy at B is delta Q into VB. Therefore, I can say I is equal to delta Q. We know that current I is equal to delta Q by delta T, or else we can write delta Q is equal to I into delta T. Change in potential energy is nothing but delta U is equal to potential energy at B minus potential energy at A. That is nothing but final potential energy minus initial potential energy. That is nothing but we are making the charge move from here to here. Correct? Now, therefore, what I can say, final potential energy is nothing but VB. So, delta Q into VB minus V of A. Let V of A minus V of B is equal to V. This implies delta U potential is equal to delta Q of minus V. Therefore, delta U potential is equal to minus delta Q into V. Substitute delta Q. So, I'll get I delta T into V. If there is no collision, then according to conservation of energy, that sentence you have to write here. If there is no collision between the charges, according to conservation of energy, kinetic energy is equal to potential energy, but minus. So I can say kinetic energy is equal to minus of potential energy. This is equal to IV delta T. But in reality, the charges will undergo collision when there is an electric field. So during the collision, the energy gained by the charges is shared with the atoms. See, one atom, when it collides with another one, it transfers its energy. The energy from one atom is given to the other atom. So there is a transfer of energy. The atoms vibrate more vigorously. When it gets energy, atom will start vibrating with because of energy given by the another atom. So what happens now? The energy will be dissipated. The conductors will get heated up because of vibration. What happens when more energy is given? It starts vibrating and heat energy is liberated. So now our conductor will be heated. So therefore, energy dissipated in the form of a heat in the conductor in the time interval delta T. So what I have to write? But when there is an electric field, charges undergo collision. During collision, the energy is transferred from one atom to another atom, and the atom gains energy and starts vibrating vigorously. Please write that sentence. Okay? What do you have to write? When there is an electric field, charges undergo collision, and hence the atoms absorbs energy and vibrates vigorously. Correct? That is, conductor will get heated up. The energy dissipated as heat in the conductor in the time interval delta T is nothing but work done. So work done is equal to what? When it is moving, Work done is nothing but kinetic energy. So I can say work done is nothing but kinetic energy. Therefore, I will write it as IV delta T. Where the small work done is IV delta T. Do you know what is power dissipated per? What is the energy? Power is nothing but work done per unit time. So work done per unit time is nothing but power. So therefore I can write IV delta T divided by delta T. So we get P is equal to IV. Understood? P is equal to IV. Or else, according to Ohm's law, we know that V is equal to IR. This implies P is equal to I square R. Correct? In the place of V, I can write IR. Then we will get I square R. Or else, according to Ohm's law, we said V is equal to IR. Correct? Then I can write I is equal to V by R. If you substitute that in this formula, then we get P is equal to V square by R. So for power loss or power dissipated, we have three formulas, that is P is equal to VI, P is equal to I square R, or P is equal to V square by R. Understood? Understood how to get this? But this derivation is not important for you. The important concept is the final formula. That's all. This derivation is not important. The important thing is these formulas. P is equal to VI, P is equal to I square R, P is equal to V square by R. Why this derivation is done? Only for your understand purpose. So what we have done? We have considered a conductor having the current, carrying the current I, VA be the potential at A, VB be the potential at B. Okay. Let VA be the higher potential compared to VB. Okay. So when there is a, what happens? The next concept what we have done? The potential energy at A, expression for potential energy at A, delta Q into V. Potential energy at B, then change in potential energy. So we can change this potential energy by using a pot. So this equipment, it is nothing but called as pot. See here, this equipment is nothing but a pot. Can you see this? We can change the equipment by rotating. Can you see here, backside? If we rotate this, the potential energy can be changed. So this is nothing but called as pot. There are three legs for this pot. Okay. Next. Now what I want to speak about is power loss can be minimized in transmission. Can we minimize this power loss in transmission? Yes, we can minimize the power loss in transmission. How can we minimize this power loss in transmission? Transmission means we are sending the powers. You are getting the power at your home by sending it from one place, correct? You are not producing any power at home. Few of you may have solar system, okay, fine. But you have to send it to all the equipments. While sending the power to all the equipments, there will be a power loss. Can we reduce that power loss? Yes, we can reduce that power loss. How can we minimize the power loss in transmission? See here, let us consider a device of resistance R. Okay, well, let us consider a device of resistance R to which the power P is delivered. For this, we are sending the power P. Through what? Through a cable. Okay, via, can I write? Via a cable. Via a cable we are sending the power. Let this cable have the resistance RC. Cable, no? So I will write the resistance of the cable as RC. Now, if V is the voltage across R and I is the current through it, if the V is the voltage across R and I is the current through it, then can I write P is equal to VI? Can I write P is equal to VI? Okay. The next, the power dissipated in connecting wires, let it be PC. Okay. Power dissipated in this cable. Power loss. Power dissipated in cable is, shall I write PC? PC is equal to I square RC. Correct, no? PC is equal to I square RC. Can I write I is equal to P by V? Then I will get PC is equal to P square RC by V square. Because in the place of I have to substitute P by V. So I'll get PC is equal to P square RC by V square. See here, power dissipated means power loss. Okay. So power loss in the cable is PC is equal to P square RC by V square. Now, V is nothing but potential difference. So if I increase the potential difference, it is inversely proportional to power. So if I increase the potential difference, then power loss in the cable is decreased. If I decrease this potential difference, then power loss in the cable is increased. So what I have to do is, I have to increase the potential. So I have to use higher potential, very, very high potential, so that I can reduce the power loss. Have you seen in some of the places, where I can see the in a junction of the power, that is in that box, that is while using high voltage danger signs in transmission lines, when there is a transmission lines, see in your nearby one junction is there where you can see transformer. From there you are getting the power supply, and it is written that high voltage, danger, some signals, one face mark and all, it is written. Have you observed? Yeah, that is because there will be a high voltage to reduce the power loss. So to reduce the power loss in the cables, we have to produce very, very high voltage. That is why we are using high voltages for transmission. Understood why they have written high voltage? See, where danger signal will be there in that box. Have you observed where there is a junction? So that is because of this, so that we can reduce the power loss. Understood? This is nothing but how to minimize the power loss. We can minimize the power loss by increasing the potential energy. What we have done, let R be the resistance of the device and P be the power supplied for that device via a cable having the resistance RC. Let V be the potential in the device and I be the current. Then I know I can write P is equal to VI. Power dissipated in the cable is I square RC. So in the place of I can write P by V. So we'll get PC is equal to P square RC by V square. So from this we can say, by using high potential, we can reduce the power loss. Understood? So now in today's class, you have learnt about the power loss expression, and also you can reduce the power loss. How you can reduce the power loss while transmission. Understood? So those three formulas are important, but that derivation is not that important. Fine? Thank you.